I updated the courseware a few minutes ago on the LMS page, which contains some of the things we'll be dealing with today. Is somebody speaking? I can't hear you clearly. I can only hear a guitar playing. Is somebody speaking or just stammering? Levi, I can't hear you. Is there any problem? Okay. Okay. We'll be talking about solids in one dimension. And like I've said in the past, the reason why we do some things, even though they are not realistic, is to use a simpler method or simpler way to approach them. When we are saying solids in one dimension, we are thinking about a world of one dimension. When we are talking about one dimension, we are talking about just a straight line. Our world in the physical space can be said it's 3D. When you are working on a surface, you can say that is two-dimensional. But when we are talking about one-dimensional, that means one dimension, we are talking about a single line. So we'll be assuming that our solids are arranged in a single line. So they cannot move in the y-axis. We are talking about x-axis, they will just be x-axis. We'll not be talking about y-axis. Though that does not really make sense in reality, but whatsoever we obtain from that reduction, whatsoever we obtain in the one-dimensional space can be easily extrapolated, easily expanded to the real 3D world that we live in. So we'll be looking at different items of solids, different items, one of which is compressibility, sound, and thermal expansion. So imagine a 1D system of atoms where two atoms are separated by a distance d. The potential, this is similar to this figure 3.1 is similar to what we noticed in the last lesson. In the last lesson, when we were talking about covalent, bonding. Let me see if I can quickly jump there. Yes, this figure 2.6, when you look at it closely, we said it is more realistic than figure 2.5. So figure 2.6 is similar to what we'll be using henceforth. And the 2.6 resembles what we have in figure 3.1. And what it's saying is that x-axis here is telling us the distance between neighboring atoms. So when we have two atoms and we are bringing them close together, the potential, as you can see, will be reducing. It will get to a time, it will reduce, and later it will begin to increase. So the work you will do in bringing two atoms together beyond this x equilibrium, because at this point where it is minimum, where the potential energy or where the potential is minimum, we've called it x equilibrium. When you attempt to reduce the spacing between the atoms such that x is less than x equilibrium, you will require a huge amount of work to do that. So it is, and if you even force it, you compress it to this level, automatically you would expect it when you remove the external force, you expect it to return to this state. Because like I've always said, that nature favors lower energy states. So at the lowest energy states here, this is the minimum potential you can have when two atoms. So it depends on the nature of the material. The X equilibrium for sodium is not the same for lithium. And this X equilibrium, they are like the spacing between two atoms. So the way we obtain this X equilibrium is we solve the Schrodinger equation to determine the point where we would have the lowest potential. The point where we have the lowest potential will tell us the interatomic spacing. So this X equilibrium gives us, is also known as a lattice constant, and it is also can also be defined as the interatomic spacing between the atoms. So, and another thing you would also notice that because we are working in one dimension, it's easy to just talk about two atoms coming together in a straight line and ignoring if if the atom has some other neighboring atoms on top or below or in front or at the back. For one dimension, we are only concerned about what is happening on the right and on the left. What is happening on the top and or the bottom is none of our business. What is happening in front and behind is none of our business. Our business is just at the left, on the left and on the right side of the atom. So the solid black line represents the potential. So this shaded, faded line is just trying to model a polynomial, a quadratic equation, trying to put a quadratic equation at the to mimic what we have in at the base here. So when we try to put a quadratic equation at the base here, this is the graph we would get when we extend it. So just to model what is happening at the base here, that is why we have the quadratic equation there. So let's move forward. So when we expand when we try to expand this equation, I will try to expand the equation of this faded or this gray line. We can claim this to be the equation. So sorry, this is a polynomial fit, not quadratic in sense, but a polynomial fit to mimic the base of the or the surrounding part of this X equilibrium. And when you look at it closely, we can say it is accurate within this point, and on getting this point, the accuracy reduces drastically. So let's just have that in mind, and let's take this particular equation 1 to represent the shaded or the gray polynomial fits we have in the graph. And the atoms we are talking about, we believe that they have in between them springs, in which when you are pushing the atoms close together, you would be pushing them against a certain force. Let's move on. So let's talk about compressibility and elasticity. I will say compressibility in the physical sense is like opposite of elasticity. So they complement each other. But when you are pressing something downwards, you can say when you are applying the force in the positive direction to change the shape of a material, you can say it is compressibility. But that same force, when you apply it in the opposite direction, it will look as if you are extending that material, no longer compressing. So compressibility, if compressibility acts on the right, when you apply that same force on the left, it will be equivalent to be elasticity. And let's bring in Hooke's law into this expression or into this discussion. When we talk about Hooke's law, it tells us that F is equal to KE. You must have heard that severally. F is equal to KE, and the E is extension. And extension is the change in position or change in length, change in length. That is extension. It's not just length, it's like a change in length, extension. Or extension, you usually call it, is it original length minus, new length minus original length, or extended length minus original length also. And K is the normal spring constant that we have in Hooke's law. And this minus here is because we are looking from the point of view of compressibility. So for higher dimensional system, we are talking about 1D, but for higher dimensional system, we'll be talking, the compressibility will be given as equation 3. And in equation 3, you'll notice that we have broken the rule of this topic, which is we have brought in volume. In 1D world, there is nothing like volume. It's only length that we have. There is even nothing like area in the 1D world, because in the 1D world, everything, everyone, everybody aligns on a straight line. So if you are aligned on a straight line, there is no point of talking about your volume. You can only talk about your position on that straight line. So let's move. So that's equation 3, which is having volume. We have corrected it to be in 1 dimension. So instead of talking about 1 over volume, is now 1 over length. Change of the change of volume to force is now change in length with respect to force. So L here is the size of the system, like a linear dimension, because we are talking in 1 dimension. So L is the size of the system. And like in our world, when you say what is the size of a box, you calculate the volume. But now all we need is the length. And the spacing between atoms is called lattice constant. And it's like a standard that we use A to represent it. Even at levels beyond these classes, A is very common in describing lattice constant. And lattice constant is the interatomic spacing, the spacing between 2 atoms for now, but later I'll be saying 2 identical atoms in a crystal. We'll get there very soon. So for a 1D system, to calculate compressibility, we have equation 4. So let's move on to sound. And in sound, I think we should I suggest you just go through that. Is very straightforward. Let's move on to thermal expansion. In thermal expansion, we would have to talk about that our graph again. Let's move on to that our graph. Okay, let us assume that we have 1 atom sitting at the bottom of this graph. So let's imagine it to be like in physics 304, they will be calling it a well or something, but let's just imagine it is sitting at the bottom of this pot. And it is being a solid, it is expected to be vibrating about its mean position. That is property of a solid. The atoms vibrate about their mean position. And when temperature increases, the atoms become more energetic. The atoms begin to have more energy. That means as temperature increases, the vibration is expected to also increase. And as temperature is increasing, it is no longer playing at the bottom, it's now oscillating to and fro, up. And as temperature increases, let's take this dotted line to be at the point where temperature has increased to. Well, if we follow the polynomial fit, we'll be saying this is how the atom will be oscillating. But in reality, well, and that is actually wrong. In reality, this is how the atom will be oscillating from here to the right, to the left, to the right, to the left. That is how the atom will be oscillating. The point I want you to notice here is that by the time this atom we said was at this point, let me take color red. We said the atom is at this point. That means that, so let me put this back and let's oscillate again from the to the left, to the right, to the left. When we come to the left, sorry, let me put something else here. Let's take another color. So it moves from the left to the right. So on coming to this left, this at a particular temperature, a finite temperature, when it oscillates to the left, it gets to a minimum distance to the next neighboring atom. When it oscillates to the right, it gets to the maximum distance from its neighboring atom. And one thing you would notice is that when it comes to the left, the distance between the x-min and the equilibrium position is very small. But when it goes to the right, the distance between the equilibrium position and the x-max is very large. So that means that it spends more time being very large compared to the time it spends being very small. So on the average, the distance of separation will be around this area. It will be greater than the equilibrium position. It will not be, when temperature increases, it will be spending more time oscillating towards the right than the time it's spending to the left. So that means that on oscillating to the right, it will spend more time on the right, and on spending more time on the right, it will be having a larger distance of separation compared to having a larger distance of separation. So on the average, because it is going to the left, coming to the left is very steep, the right is very slant. So on the average, the length of separation on the average will be greater than x equilibrium. And that answers the question of why is a material, why do they increase in length as temperature increases? Why do they increase in length as temperature increases? The answer is because when the temperature increases, their vibration also increases. The oscillation increases, but they oscillate away from themselves compared to oscillating closer to themselves. So that gives them an average length that is greater than their normal equilibrium position or their normal distance of separation. I hope that is clear. Do you have any question on what I've just said? Okay. Silence means consent.
No, sir.
Okay.
Sir, can you repeat the sentence you made just now?
The sentence I made just now is that
the temperature.
I said as temperature increases, as temperature increases, the vibrations of the atoms also increases. Their oscillation also increases. Because I started with saying the property of a solid is that they vibrate about their mean position. I'm sure that is one of the elementary definitions of a solid, that they have fixed volume, they have fixed shape, and the atoms vibrate about their mean position. And the point is, as temperature increases, the vibration also increases. As temperature increases, the vibration also increases. So when this atom wants to vibrate, that is sitting at the equilibrium position, that is having a distance x eq from its neighbor, when temperature increases, it will not just increase in length, it is its vibration that will increase. It will not just increase in length towards the right, it will be oscillating to and fro. It's the vibration that will increase. And when the vibration increases, it means that the separation between the two neighboring atoms, the separation will increase to this point, and also contract to this point, expand to this point, contract to this point. So we are taking this particular point, a particular temperature, kBT, to just like reference. So the atom that was sitting here before, having absorbed the energy as a result of increase in temperature, begins to compress, expand, compress, expand. The length of compression is very small. The change in length as a result of compression is very small compared to the change in length on expansion. For that reason, we can say that the average position would be greater than x equilibrium, because when it compresses a little below the mean position and expands greatly above the mean position. Then we can say that the average position, as a result of increase in temperature, as a result of expansion, would be greater than xeq. And that means that we would have expansion and not compression. I hope that's clear. Can we move on? Silence means consent.
Yes, sir, we can move on, sir.
Okay.
Yes.
Okay. So let's talk about vibrations in a monatomic chain. So when we are talking about a monatomic chain, we are talking about some particles, or you can call them masses. They are, for simplicity, they are identical. They are identical. In fact, because they are identical, that is why they are monatomic chain. If the atoms are not identical, we will say diatomic chain. But in this case, to find their monatomic chains, and they have a mass m, and they can be said to be connected by springs of spring constant kappa, and the distance of separation between each of the particles is the lattice constant A. So the same thing applies all through. The distance between this and this is A. The distance between this and this is also A. The distance between this and this is A. Their masses are M. The spring constants of all the springs in this diagram is kappa. So now we consider a 1D monatomic chain comprising of identical atoms and mass separated by a distance, connected by identical springs. So just like we had in that graph, A is as good as the A we have here is as good as we saying that X EQ. And in this case also, we should try to label these atoms or these particles. We can label them such that we'll say this is at position x1, this is at x2, x3, x4, x5, and on and on and on until we get to xn. So the index of this each of the positions, they are usually integers, and we can just be calling them n to depict a particular atom. So just like I've written here, the equilibrium position of the nth atom is represented by xn equilibrium. So for a particular atom, if we take any of the atoms and call it the nth atom, the equilibrium position is xn equilibrium. And we should also remember that for the fact that that is the equilibrium position does not mean that that is where we will always find them. It means that that is the average, like on the average, a location where you will possibly find them, because they are there, but they are vibrating. They are shaking to the left and to the right. They are vibrating, and the vibration depends on the energy absorbed. Okay. So the particular location of at a particular time, you will be describing it as x subscript n, but the equilibrium position is x n equilibrium. So when the motion of atoms take place, the displacement of the nth atom, that is final position minus equilibrium position, is defined as NA. So NA, in the sense that, let's take our N to be 5 in this situation. Let's take our, okay, let me use 4. Let's take our N to be 4 in this situation. That means that the X4 will be equal to 4 times A. And what does that even mean? It means that from this point to this point is having distance A. Here to here, also distance A. Here, this point to this point has been labeled as distance A. But from the zeroth atom to this point, we can also call it distance A. So from the origin at x of 0, which is at the origin, from the origin to x4 to the to x4, we will be having A plus A plus A plus A, which will be 4A. So and that tells us that a system of n atoms will have length Na equal to xn equilibrium. So when we are talking about n atoms, just like we are having n atoms here, the total A we can have here will be n times A. And what is our n? If we'll be realistic here, our total n, our n here is 6, and the total length would also give us 6A. Since the distance, okay, I think I've said that over and over. So let's move. Okay. Hello, can you hear me?
I can hear you, sir.
Okay.
Oh, we can hear
Okay. Well, because I'm connected via MTN, my MTN line, and somebody is now trying to reach me on that line. And I noticed that disrupts the class. Okay, so we have a potential defined in equation 3.7. And from the potential, it's just like we have when we are talking about Hooke's law, and they say what is the energy saved in this spring. Yeah, I'm sure you still remember something like you used to say something like, I think half kx square, right? But in this case, we are okay. Half, let me write it this way: half k x square. This is usually the formula we use in secondary school when they say energy saved in the string. And this, but for this class, we'll be using kappa, not just k, because k is a wave vector. We have chosen k to be wave vector, so we'll be using kappa to be the spring constant. And this x is not really x, it's usually it should even be dx, because extension, because okay, sorry, it's usually call it e square, so e is extension, so the extension is as good as final minus initial length. And for that reason, we'll be considering a particular form of expression. So we'll be treating it like we are having three atoms. So we call this xi. We call this xi minus 1. We call this xi plus 1. And when we want to talk about the how can I make it simpler? Please, 1 minute. Let me go. I think I have to make reference to my class notes. I think it's simpler to use my class notes to explain better. Yeah. So when we, okay, let me try to wipe this off. So I would think about an atom. I will call it we said it's at position x1, and it displaces to the left. When it displaces to the left, we can say that it is now at position, when it displaces to the left, we can say it is now at position xi xi minus 1. When it displaces to the right, the same matter, when it displaces to the right, we can say it's now having a position xi plus 1. So when we are now talking about the actual displacement, we should be talking in terms of xi plus 1 minus x1. And also that is xi plus 1 minus x1. We can also talk in terms of the displacement to the left to be something of the form xi minus xi minus 1. So the displacement of the first one, we can represent it as xn plus 1, while the other one as xn minus 1. So when we try to insert into this equation to say that the force, as just like Hooke's law, to say that F is equal to kappa E, we'll be talking about the extension to the left and the extension to the right and the extension to the left. The extension to the right is as good as when it moves from this point, to this point, and the extension to the left when it moves from this point backwards. So we'll be talking about xn plus 1 minus xn. I think this one should be xn minus 1. I will look through this and get back to you. So, okay, no, it's correct this way. It's correct this way. Then when we simplify this expression, we can open this bracket and collect like terms. We would have the last expression here, which is equation 3.8. But the only, one of the major things you should notice here is that F is equal to KE is Hooke's law. F is equal to MA. That is Newton's second law. So we'll now be relating MA, because these two dots on top of X here is telling us second derivative with respect to time. So this is like so this is MA. So MA is equal to KX, just like you're used to, or KE. Sorry, let's use KE. But now our K here is kappa, not just K. So F is this is Hooke's law. This is Newton's second law. So because we can also relate the extension and the motion of the atoms to mean second law of motion, the atoms are moving as a result of applied forces. So now the problem at hand is to solve this particular equation. And to solve this particular equation, we bring in a trial solution. And the trial solution is saying that because we are interested in just removing this F, and now say that we have a new expression and we are interested in having X. What is our delta X? Now we are having the square X, the T square, and we are interested in delta xn rather. So the trial solution that is adopted is what I have in equation 9, and X equilibrium. The only difference here is that X equilibrium is as good as product of NA. So that's we've said that before. So you can, if you want to go through the steps, that's straightforward. Okay, so from the previous expression, our A, the constant A, just like we have in this expression, the constant A is the amplitude of oscillation. K is wave vector. K is wave vector, while omega is frequency. And N is like is an integer which tells us the particular atom or particle we are referring to. So for this, to find a solution, we restrict the omega to be greater than 0, because it doesn't even make sense for you to have omega that is less than 0, since omega is a frequency, the number of angular frequency. But let's talk about it about like frequency, number of oscillations you have in a second. It doesn't make sense for you to say that you are having -5 oscillations per second. So on a clean slate, omega must be a positive value, but K can be either positive or negative. When K is positive, it means that the wave is traveling on the positive x-axis, but when it is negative, it means that K is traveling towards the left on the negative x-axis. Okay. So this equation is as good as the previous one we had. Let me bring it back. When you look at equation 3.8 closely, we are talking about MA equal to, we are talking about MA, that is Newton's second law, being equal to Hooke's law. And now our the x here is now taken to be equation 3.9. So we'll be bringing in equation 3.9 to mean x in this particular expression. We're bringing in equation 3.9 to mean delta x rather in this particular expression. So when we do that, that will mean that where we add MA would mean that where we add before we add something like MA equal to F equal to kappa E, or kappa E. Yes, let me use E for extension. Now our A, which is as good as d square x d t square, would now be taken to be a second derivative of the trial solution that we have here. For this particular expression, when you differentiate it with respect to time, when you differentiate this particular expression with respect to time, when you differentiate with respect to time twice, then you can say that you have the what do we call it? You have the acceleration, or you have the delta x dot dot, and that can be easily substituted into that can be easily substituted into this particular expression, into equation 3.8. That can be easily substituted into equation 3.8 to give us equation 3.10 rather. So the first line we have in this expression is as a result of we having differentiated, so this is as good as having differentiated our trial solution with respect to time twice, and we now multiply it by A. So I will our trial solution, which was telling us that X is equal to A I K N A plus I omega T. It is now, when we differentiate that, I will substitute as in the Newton's second law. We have what we have in this green box. And when we try to do the same thing for the expansion or the extension of the spring, we'll be talking about in terms of that is the Ohm's law. We'll be having the spring constant and the new extension as a result of the trial solution. So if you want to play with this one at your leisure time, you can try to replace the delta x dot here with the second derivative of 3.9 with respect to time, multiply it with m. You would have minus m omega square a, all this, and this expression again. And you can also come here to say that in place of x delta xn, you want delta xn plus 1. So wherever you have n here will become n plus 1, and you put it to represent delta x subscript n plus 1 here. Wherever you have delta xn, just like you have here, it will just come in here straight away and just have it multiplied by 2. And wherever you have delta x subscript n minus 1, you would have to put in this same expression, but instead of you having just n, wherever you have n, you replace with n minus 1. And by doing that, you would have equation 10, which is given here. So from equation 10, everything that follows is mere simplification. Everything that follows here is mere simplification, in which we collect like times, they cancel out, we get to this point, and when we get to this point, we'll be talking in terms of the relationship between exponentials and trigonometries. When you are talking about exponentials and trigonometries, I think there is a relationship that tells us that e to the I think e to the I theta should be equal to cos theta plus I sine theta, and e to the minus I theta should be equal to cos theta minus I sine theta. So when you expand this exponential IKA and exponential minus IKA, when you expand them in terms of this theta, so wherever I've put theta here, you replace with KA. So, or do we need to do that? So if I erase this. So when you put e to the IK into this expression and e to the minus IK, when you put into this expression minus 2, you should get 2 minus 2 cos K. And okay, sorry. You should get 2 cos KA. You should get 2 cos KA minus 2. But by the time you now divide by minus m, then the minus sign will affect the signs of the cos 2 cos k and the minus 2. Then you now have 2 minus 2 cos k. So, and the dividing by m brings kappa to be kappa divided by m. And working around this 2 minus 2 cos ka, when you take it to trigonometry, you should 1 minus cos ka is as good as is that not this sine square? Okay, I think let's try to derive something. Cos 2 theta is equal to cos square theta minus sine square theta. And cos square theta is as good as, or let's say sine square theta. Sine square theta is as good as 1 minus cos square theta. That's equal to minus 1 minus cos square theta. And that is as good as we having cos square theta minus 1 plus cos square theta. And that is equal to cos square theta, 2 cos square theta minus 1. Well, we have 2 cos square theta minus 1. We can also work around this cos square theta and call it 1 minus sine square theta minus 1. And that is as good as 2 minus 2 sine square theta minus 1. And that is as good as 1 minus 2 sine square theta, right? Yes, 1 minus 2 sine square theta, yes. And when you want to look at it from another dimension too, if everything we have written here, if it is equal to, it's equal to cos 2 theta, then what is cos theta? Then we can say our cos theta will be equal to 1 minus 2 sine square. Instead of we having theta, it will now be theta over 2, because before it was formerly cos 2 theta that gave us 1 minus 2 sine square theta. So that means cos theta should be 1 minus 2 sine square theta over 2. So, and that is the origin of we having this second line. So you can, that may be useful if you want to go through it at your leisure time. So, and the omega we have here is as good as square root of both sides. And we have the absolute value of sine Ka over 2. And the reason why we have the absolute value of sine Ka is because sine is an odd trigonometry. Sine is an odd trigonometry. When you do something like, how do I explain odd trigonometry? When you, this thing they taught us in secondary school, they draw something like this and they say, everything here is positive. I think they say sine here is positive. I'm not, I think this place should be tan, everything tan. Okay, I think this is it. Yes, I think something like this. When everything here, when it starts here to be 0, and you move towards this place, you say this is 90 degrees, or pi over 4. Sorry, pi over 2. You get to this place, they say that is plus 180 degrees, or pi. You get to this place, they say 270 degrees or 3 pi over 2. And coming back to this particular point. So when you are talking about odd trig and even trig for sine, for instance, I will say sine 30. Sine 30 should be something of this nature. This should be sine 30. And when we are saying minus 30, you should go in the opposite direction. This should be minus 30. So when we say the wave is traveling towards the right, we can say K is positive. When it is traveling to the left, we can say it is negative. Is somebody saying something? So when the wave is traveling towards the right, you say it is plus 30. When it is positive, when it's traveling towards the left, it is minus. But when we attempt to calculate the sine of sine 30, we get a positive value. And when we say sine minus 30, because this is the domain of C cosine, we have a negative value. But for cosine, when we say cos 30, we have a positive value. But when we say cos minus 30, you still have a positive value. So that is why you can say that cosine is an even trigonometry. Cosine is even while sine is odd. For the fact that cosine is odd, and we are talking about the angular frequency, then we should be careful with the the sign. So we don't want to have anything that will give us a minus value as a result of the sign, because K can be either positive or negative, and we don't want anything to affect the sign of this sign. That is why the absolute value is required. If it were to be cosine, you wouldn't need this, because cosine, be it positive, cos a positive number is equal to cos a negative number. So there is also something that we call dispersion relation. Dispersion relation. When we're talking about dispersion relation, we are concerned with. Let me bring out this pointer. We are concerned about the relationship between the frequency and the wave vector. So when the wave vector is 0, the angular frequency is 0. And when the wave vector moves towards the boundary, because in this case now, we've said earlier that the atoms are separated by a distance a. And now from the dispersion relation, it has been observed that at the boundaries, that is from minus pi, we observe that from the origin, when from our expression, from the expression we've just obtained, from this the graph we have below is like you plotting equation 10, and when K is equal to 0, omega will be 0, and when K is equal to minus pi over A, omega will be maximum. And when K is equal to plus pi over A, omega will also be maximum. So, when that happens, we have this shape, which is the dispersion relation. And this minus pi over K to plus pi over K, it tells us that the length, the distance from this point to this point is 2 pi over A. Let me use a different color. Two pi over A. So for our atoms which were said to be spaced, at a distance A, when we talk about their wave vectors can be said to be spaced with an arbitrary separation 2 pi over A. So, well, in the direct world, in the real world, those atoms are separated by a distance A, but in another world, which we call the K space, the separation is 2 pi over A. And in that other world, K equal to minus A and K equal to plus A are said to be the boundary of a particular atom. You see, when we say this atom, okay, when we say we have 3 atoms, or 4, or 5, we can say that each of these atoms are separated, have their own. It's like each one having their own room. So just like these green dotted lines, they are like they are separating each of the atoms into 2. So I don't expect you to argue with me if I say that the distance of separation between these 2 green lines will also be A. I don't expect you to argue if I say that I have put dotted lines in between these red atoms, and since the red atoms have a lattice constant A, and we now put perpendicular lines to cut in between at the midpoints of each of the atoms, then the distance between these perpendicular lines should also give us A. So the distance between the midpoints between these atoms can also be said to be what we have here from this point. From this point to this point. So just like we have the distance of separation here to be A, in the K world, the distance of separation is 2 pi over A. I must apologize that in this part of science, there are a lot of things you have to imagine. Not everything is direct and real, but the applications are actually direct and real. But you have to imagine a lot of things. Now, we'll be talking about atoms. We'll be talking about the distance of separation, but we want to go into something I will call like another realm, where we'll be talking about the K space. We're talking about something in another arbitrary world, which is which we'll be talking in terms of the wave vector K. So in this our world, we talk about distance as lattice in terms of lattice constants. We will talk about atoms being separated with a distance A. We talk about atoms being separated by distance A. But in this new world, we talk about these arbitrary atoms being separated by 2 pi over A. And that word is called reciprocal lattice space. I think we should get there. If not directly now, it won't be long that we'll get there. Okay, I think we are there already. So so far, we have been talking about atoms, their distance of separation, but now from our dispersion relation curve, where we now have a graph moving from minus pi over a to plus pi over a. That is like a proof that there is a particular world which is just like we have our real space here with periodicity A. Then in that world, which is the reciprocal lattice space or K space, their own is periodicity 2 pi over A. And the name reciprocal, when you look at the distance, it's A, but here we're having a constant divided by A. So it's like a reciprocal of length. So one over is as good as a constant over length, a reciprocal of length. So that is where we can say they got the name reciprocal. But anything other than the name reciprocal, we'll be using K space so much because 2 pi over A is as saying 2 pi over length. Or if I don't want to use length, I will say another length that we use often is lambda, which defines wave vector. So we'll be talking about K space and the likes. And one thing I want you to also notice that in that our dispersion relation curve, where we said this is the origin, and okay, let me make it a bit smaller. We call this wave vector. We call this angular momentum. It is actually something like this. So this is like 0, and the distance of separation at this point. Oh, I should have used another line. This is minus pi over a. This is plus pi over a. So that means that this place should be 2 pi over a. This place is minus 2 pi over a. This is minus 3 pi over a. And this is plus 3 pi over a. So what we have within this region, everything we have within this region is called the first Brillouin zone. From the second pair of dotted line, let me see if I no, that's not feasible. So from the second, from this point, let me put it here. We called it the first Brillouin zone. From this to the second, from minus 2 pi over a to plus 2 pi over a, it's called the second Brillouin zone, while from minus 3 pi over a to plus 3 pi over a is called the third Brillouin zone. Somebody is writing in the chat box. Please speak out. Okay, let me see. Maybe, but why your why? I don't understand. Boluatife, what are you trying to say? Boluwatife, unmute yourself and speak. I don't understand what you have posted. Boluwatife Oyebamiji. Okay. I hope you can see what I've written on the screen. I hope it's not complaining about what I've written. But I wonder why is it not speaking up? Boluwatife Oyebamiji. I will take him as absent. Hello, is there any problem with so far? Do you have any problem? Okay. So, in the real space, we speak about having positions xn, while in the reciprocal space, we talk about having positions gm. So, and in when we have atoms, separated by in the real space separated by distance a, we can easily say that we can pick one to be at the origin. I will say this is at point A, this is at point 2A, this is at point minus A, this is at point minus 2A. I think it's reasonable to say this, that these atoms, they are separated by distance A. Well, we'll put the middle one at the origin. Then those on the right can be said to be on point A, point 2A, just like we are talking about Na being equal to n times A, being telling us the position of a particular nth atom. But in the reciprocal lattice space, we'll be talking about this being in the origin, but this is at k point 2 pi over A, and this will be 2 times 2 pi over A. This will be minus 2 pi over A, and this will be minus 2 pi over A. So, and I exponential I gm xn gives us 1. So that's like a rule of thumb. We'll be using it to simplify as time goes on. That is the position, the exponential position at position at reciprocal lattice space times the corresponding position at real space should give us 1. I'm thinking of us playing with this particular expression. Let's talk about it. E I gm xn can be said to be equal to, let's take for instance, let's just take these two for instance, this and this. That should be what is gm minus 2 pi over a, and xn minus a. So, and this will give us ei 2 pi. And I will say ei 2 pi from what we have spoken about exponential I, which is as good as cos 2 pi plus I sine pi, sine 2 pi rather. What is cos 2 pi? Cos 2 pi is as good as cos 0, which is 1. And plus I sine 2 pi, that is as good as sine 360, that is 0. And I think that gives us what we have here. So I suggest if you, when you are less busy, you can play with each of these equations, trying to get the next equation after the other one. That is how you enjoy science. But the course material I've given you, if you sit down on your bed and you read them, you may find them okay. But if that is all you do, you may have problem along the line when it comes to examination, which is very important. When it comes to examination, some things that I'm doing right now that you are looking at it that yes, it makes sense. So you are now asked to do it independently. You may get stuck if all you do is read and you don't write. In science, especially in physics, we don't understand by just reading. You understand by reading and writing. So I hope I've passed the message anyway. So this figure is trying to tell us that compare two different types of graphs, where we have one that is of wave vector k, and the other one is wave this. Okay, let me bring out my pointer. This is wave vector k, while this is wave vector k plus 2 pi. And the point that this graph is trying to show is that k and k plus 2 pi will always agree at the lattice points. This is this is like a direct this is a direct space. So, but at the lattice point, this is 0, this is A, 2A, 3A, 4A, 5A. So at these points A, that is where we have atoms, because we said atoms are separated by a distance A. We have one here, we have another atom here, we have another atom. So, but at this black spots that they've put here, there are points where the dashed line and the solid line, where they actually agree, where they meet and they agree. And when you look at it, at the origin, they agree. At the first lattice site, they agree. Second lattice site, they agree. Third lattice site, they agree. Fourth lattice site, they agree. So that means that when we are moving from atom to atom, as moving distance A, like a periodic motion, moving at a certain distance A, an equivalent in the reciprocal lattice space is to be moving in 2 pi over A. Moving in 2 pi over A is an equivalent of moving in 2 pi. Also, it's an equivalent of moving in A in our real space, in the real world. Sorry, I would have to, I'm just noticing something here. This should be in figure 3.4. To be in figure 3.4. So the text is written in LaTeX. So I think I should have compiled twice to show this as figure 3.4. So when we talk about properties of dispersion, in the graph we have seen, we'll be talking about that sound waves have this should be have long wavelengths compared to interatomic spacing. In the long wavelength regime, the dispersion is linear with wave vectors. In the long sample, okay. So in the long wavelength regime, dispersion is linear with wave vector. That is, you must have seen this expression before. Must have seen this expression before, which is saying that dispersion is linear. And but from the graph we have plotted, which we have shown, which tells us something like this. Here we say this is omega, this is k. You would notice that the dispersion is not linear. You notice that this expression is only valid for small k. When you move, when you for very small k, you can say that this is linear, this is linear. But when k increases up to this level, this is no longer linear. So this expression is just like an approximation. One of the things they have we have said just to make things easier. So, and at large k, sound waves is no longer linear at shorter wavelength. So short wavelength means large k, because I think I said something recently where I said k is 2 pi over lambda. So when we say large k, we are talking about small wavelengths. And when we say small k, we are talking about large wavelengths. So at shorter k, we define two velocities. So which are group velocity and phase velocity. The speed at which wave packets move, that is v, this should be no subscript group. Sorry. This should be no subscript group is equal to the omega decay. We also have what we call phase velocity, which is the speed at which individual minima and maxima move, which is no subscript phase, and it's omega over k. So this is the omega decay, this is omega over k. And these two velocities match only in the case of linear dispersion. So that is the match only at small k. The group velocity becomes 0 at the Brillouin zone. I think I've mentioned Brillouin zone for us. So for you to understand this, what we mean by group velocity and phase velocity, I don't know if you did that in 200 level, but you can, I've put a Wikipedia link here, which you can click to access. And I may need to mention that Wikipedia is like a collaboration of the entire world. Everybody, you can just open an account on Wikipedia today and add anything there. So you the things you find there, their reliability depends on other people reading what others have done. If you make in this link I've clicked, I saw an error there. I corrected it because I edit Wikipedia, and if I had just asked you to go there without me even checking it myself, what you would have found there may have been misleading. So I found an error there. I corrected it before asking you to go there. Another person can just go there and correct it or to mislead by changing it back to something that is wrong. And when that happens, that reduces the credibility of Wikipedia. But to also increase it is that other people are also reading. And when people that are unserious go there to mislead others, some people are also watching to set the facts straight. So let's move on. Or should I even add that there is a Wikimedia club on campus? If you want to join, I'm a member, you can just you can send me a message, and I'll direct you to the coordinator. So in the club, they will teach you how to edit Wikipedia. That's just a simple description. So let's. Hello, someone is speaking.
I think will they pay us if we join this stuff?
Are you guys? No, they won't pay you. Let me answer your question straight away and not waste my time. It's a voluntary stuff. They don't pay you. So, but you would develop yourself somehow by writing. And what do you write? Different things. If you are the one that likes sports, you can write about sports. If you are the one that like movies, write about movies. So it depends on different things. So, but they don't pay you. But it's there is something called Wikimedia Foundation, which if you are active and you belong to a club like that of UI, you can have some benefits too. They can sponsor your trip to Wikimedia conferences. That is all I know for now. They sponsored my trip to Lagos for once and accommodated me for about, is it 2 or 3 days? I can't still remember. When it was time for Abuja, it wasn't chance for things like that. But it's currently on campus and it's a bit organized. And if you're interested, but if you want to join for the knowledge, join for the relationship, not for money. If you wait for that one, you may get frustrated. Okay. Let's come back to physics. Counting normal modes. So when we've spoken about periodic boundaries in the past. So now will be just like a classical way of viewing vibrations is what we want to do here. Trying to count vibrations in a classical way. So when we we use periodic boundaries, assuming that we have a system of n particles in a row where the particle x0 has x1 on the right. So we have a particle, we have a particle x0, which is having x1 on the right, and xn minus 1. So this is like x1, xn minus 1, big N, because there are big N particles in that row. Okay, I'll try to round off very soon because I think you also need to rest. So it means that this particular particle can be said to be x0, at the same time can be said to be x big N. So let the 1D system form a circle. We have done that before when we were talking about periodic boundary conditions, where we spoke about having a length L forming a circle such that when you move through the circle once, you get to this point. So when you take another arbitrary point, from this point, when you move through the circle, or when you move from this point plus length L, you return here, plus length L, you return here. So something similar here now. When you say this is x0, which is the same as xn, on the right, we have, big N. We have x1, x2, x3, x4, x5, and x6 is the last one, which is xn. So we have n particles here. Ganil, Rafiu, what do you have to say?
Well done, sir. Sir, please, can that of counting normal modes, please, can you explain it, sir? Counting normal modes, sir.
Yes,
Please,
that's that's what we are saying currently. That's where I am. I've not left counting normal modes. Okay. The only thing I said was we have spoken about periodic boundary conditions where we have we talk about a particular length L.
Okay, the beginning and the A1 and the right hand side.
Yes, okay.
Yes,
okay, we are talking about this point. Okay, I think I now get to this. At this point, I'm reading what we have here. We use periodic boundaries, assuming that we have n particles in a row, where particle x naught, so this is my x naught now, or this is my x naught. It is having x1 on its right hand side.
Okay.
And xn minus 1 on its left hand side. So this x5 is as good as xn minus 1, because this our x naught is also as good as our xn. So what this is telling us that when we are at position 1, when we want to, and from, okay, let's just write one origin here, which is saying that n is equal to 6. I think we have 6 particles in this particular line. So from this particular point, is that cock just waking up at to 2? So at this particular point, x2, when we count 6, 1, 2, 3, 4, 5, 6, we come back to x2. When we count 6, 1, 2, 3, 4, 5, 6, we come back to x2. When we are at x3, when we count 6, 1, 2, 3, 4, 5, 6, we come back to x3. So when we count anything n, when we count 5n, that is 5 times 6, 30, from this place, when we count 30, 1, 2, 3, 4, 5, 6, 7, when we get to 30, we will still come back here. So that is just that's just a simple difference between this circle and the previous one I've shown when we are talking about periodic boundary conditions. That should be, should be lesson 1. Yes, should be lesson 1. Okay, I think we are free. So now let's look at this expression closely. This expression, exponential I omega t minus I kna. So this, our particular n, we can replace it with big N plus n. So at where small n at this point was 3, our big N plus n, maybe in this case, will be 9. It can be, so when we are talking about x9, we'll come back to x3. So, and we can also say that exponential ikna should give us 1. So this restricts the number of k. So our k must be of the form 2 pi n over a, or 2 pi n over L. So in this case, n must be an integer, L is the size of the system, and k is also having the form of 2 pi over lambda, which is the form of wave vector. And k is quantized, it is not continuous. There are discrete values of k that you can have also in the reciprocal space. Just like when we want to count in the direct space, we can say we have 5 atoms, nothing like 5.3 atoms. The same thing in the k space, it is quantized. K has specific valid values, not just you saying any arbitrary value. Innocent.
Sir, please, we do have a class 15 minutes from now, and then we need to. Yeah.
Okay. I think I said something like that just now. I will stop at this particular line. Let me draw a line here. I'll stop here. The rest are things you can read on your own till we meet on next week. So the total number of modes is equal to the range of K divided by the spacing between neighboring K. So what is the range of K? The range of K is 2 pi over A, while the spacing between K, which has been derived at equation 13, so that gives us 2 pi over A divided by 2 pi over NA, which directly gives us N. Or if you want to go through the long route to say 2 pi over A is L and 2 pi over NA is A. So but by dividing this straight away, you have N. So we have one normal mode per particle. So that is just the conclusion we have here. So I suggest you read through quantum modes. It's very short, but the long and short is that just like we have photons in light, we have phonons for vibration. So the photons in light is trying to talk about light as a particle. So also the same thing, phonons in vibration is trying to talk about light as try to talk about vibration like a particle and not wave. Okay, and they're also quantized, so you can just go through them. So when we'll meet next week, we'll be talking about a diatomic chain. Today we are talking about monatomic chain, where all the atoms are identical. But next week we're talking about like a new type of system, for instance, sodium chloride, where we have sodium and chlorine on the same line. So forming a chain. So what would be the dispersion relation? So we're talking about that next class. So sorry for taking too much of your time. Have a great day. I hope there is no question before. Okay, bye-bye.